Okay, so I will talk today about our recent experiment on evaluation of looking at cracking mechanics with image correlation that we've done in collaboration with Mohammad Zanganet from America and our group at the University of Malaga. So there exist a few full field techniques that for evaluating cracking mechanics in general, or the stress intensity factor in particular, including caustics, Moore interferometry, thermoelastic stress analysis, or photoelasticity. They've been used in the past for evaluating the stress intensity factor, but they all have some restrictions. So for example, photoelasticity requires a refrigerant material, or thermoelastic stress analysis requires a specific loading regime, and so on. And on the other hand, image correlation is more versatile, cheaper. It doesn't have all these requirements, and probably because of that, it has been used in the past, in the past decade or so, quite a lot for evaluating the stress intensity factor. It started being used to evaluate the stress intensity factor in artificially generated notches, and then, they started working on, they were able to predict the stress intensity factor, to estimate the stress intensity factor in real fatigue cracks. First in pure mode 1, then mixed mode. Then the methodology also moved towards monitoring the stress intensity factor and correlated with crack growth. Just simply by looking at a sequence of displacement fields, and then this field, it was possible to evaluate this the field different steps through the loading and unloading to basically correlate, estimate the stress intensity factor and correlate it to the growth. And if you use a standard camera, you can do a low frequency analysis. And if you do if you want to study just normal low frequencies, you need a high-speed camera. The methodology has been also used to evaluate more complex geometries with non-uniform passing stress fields, which have more industrial relevance, and then also combining different mode mixities, mixed modes of loading. And the methodology finally has also been applied to evaluate the stress intensity factor to real aerospace component. So it seems there is quite a lot of work on evaluation of stress intensity factor from image correlation, but each of the works uses different parameters. So they use different field of views, different magnifications. The crack is sometimes inside the image, sometimes it's outside the image. So the idea of this work is to sort of come up with some guidelines so that we can try to unify that. Of course, that will depend strongly on the geometry that we use and the loading conditions. So this is, from that point of view, it's a preliminary work in that sense. So the idea is all these works are basically based on the multi-point over-deterministic method that our colleague from Urbino has been introduced before. And we basically have an elastic model describing the crack tip field, and we fit that model to some experimental data point, in our case displacement data point. And then depending on which model we use, then we can can use Westergaard's solution, Williams expansion. We can use Muskel's-Billy's model, or more sophisticated approaches such as the Christopher James Patterson model that can take into account not only the driving force but also retardation forces. So what we are trying to do is to look at, see if we can find some image, some magnification level which will be closely related with the field of view. Also trying to see what's the best place to have the crack tip inside the image or outside, and all the parameters such as the interrelation, window size in the image correlation, or in the case of Williams expansion, the number of terms. We've used, so to do that, we've used a compact tension specimen made of aluminum alloy 2024, and we used different lenses trying to cover like a very wide range of magnification, and we were able to get from using the long distance microscope with a higher magnification. We were able to do image correlation on a small patch of 0.6 by 0.6 millimeters, and we were changing the lenses. We were able to go up to 20 by 20 square millimeters. Of course, at first, if we want to evaluate the stress intensity factor, one could think, okay, well, just get data from the K-dominated zone. But in the case of image correlation data, this is not so easy. So we have the crack tip, then we have the plastic zone, and then surrounding the plastic zone, we've got the K-dominated zone. But we cannot really, in an easy way, or at least I don't know how to get this K-dominated zone from the displacement data. So we did, to start with, we did like a very coarse approximation. So DIC gives us displacement data, and we can numerically differentiate this displacement data to get the strain data. And then of course we have strain data which is already quite noisy. But still, we can say that that's roughly okay. So if we, from this strain data, we get the stress data, and we are assuming here elastic behavior, which is not going to be correct. But I guess our idea is that we are trying to get like a rough estimation of the dimension that we should use. And that was around 1.2 millimeters. So with that figure in mind, we did a few tests covering, from 0.6 to 20 millimeters. And we evaluated the difference between the theoretical stress intensity factor evaluated following Urbino's handbook and the experimental stress intensity factor evaluated with the multi-point over-deterministic method. And we can see, here we have the results. We can see that, the first thing is that if we use one term in Williams expansion, the best result is obtained with the smallest field of view, which sort of matches thinking that this field of view is, roughly it's going to be similar, it's going to be the size of the K-dominated zone. As we increase the number of terms, of course we need to take into account a larger area, and we can see that phenomenon here. We can see that, for example, if we use 3 terms, the best predictions are obtained with 12 millimeter field of view. So not so close, so collecting images not so close. And we can also see that this, by having a larger field of view, the resolution is actually better. So if we not only take a singular term, but all the additional terms, the resolution for evaluating the stress intensity factor improves. We were also interested, as I said, in knowing what's the best, where shall we have the crack within our image. For doing that, we evaluated the parameter lambda, which is basically the length of the crack that is included in the field of view. So, for example, this would be 25 lambda equals 0.25, or 25% of the crack is inside. 25% of the field of view is we have the crack inside, or if we have the crack tip right in the middle, we will have lambda equals 0.5. And the results we got was this one. Again, we are showing the difference between the theoretical and the experimental. We can see that the smallest, so the best predictions are obtained for lambda equal roughly 1/3. So 0.33 or something like that. So this means that we will have to collect not only, so the best predictions for this case are obtained collecting data not only from ahead of the crack tip, but also from behind, which is like often like you see some works where data are collected only ahead of the crack. Well, if we use image correlation, according to this result, it looks like it's better also to include some data from behind the crack tip. Probably due to like better signal to noise ratio that we have, well, in the back of behind the crack tip. And finally, we were interested in looking at the effect of the subset size. So for the algorithm, the image correlation algorithm, we have to evaluate the interrogation window over a certain size, and then, well, does that affect the results? And we found that, again, we are showing the difference between the theoretical and the experimental stress intensity factor against the subset size, and we can see that, well, for the different magnification is pretty much stable. We don't get much better or worse results by changing the subset size from around about 20 pixels to 150. So, to conclude, I would like to say that, well, the best results were obtained with a magnification such that the field of view is 12 millimeters, using not just one or two terms, but 3 or more terms gives the best results. The crack tip should be located in like 1/3 of the image, and we have observed very little influence of the subset size. Of course, this is a preliminary study, so we should really complete it with doing basically a similar study to more crack lengths, more geometry, loading conditions, and so on. Thank you very much for your attention.
Thank you.